Hello everyone. Today I would like to discuss our attempt to improve interprocedural analysis for Clang static analyzer and also discuss our implementation, our achievements and the work that should be done in future. Clang static analyzer, or just CSA, is a part of Clang. It is a path-sensitive source-based analyzer for Objective-C, C and C++ code with the ability to perform context-sensitive interprocedural analysis. It has a simple but powerful checker API as well. And our talk is devoted to the improvement of its API. Clang static analyzer simulates the execution of functions from a given translation unit with symbolic input data. It explores the path inside the function with building a graph consisting of program states in different program points and transitions between them. And this graph is called exploded graph. On this picture, we can see the example of some states which may be discovered during the analysis of our test example. In Clang static analyzer, state of the program is represented with three items: the store, the environment, and the generic data map, or just GDM. The store maps memory regions on symbolic value that's stored in them, and it represents the contents of program memory. On the sample, the store is represented with writes to a global variable C, so it has different values on different execution branches. The environment maps the set of active expressions on the symbolic values they have as the result of our simulation. And finally, the generic data map is a multi-purpose container which consists of different traits, and it is extensively used by analyzer checkers and some analyzer engine functions. Analyzer checkers usually subscribe on some events and operations and check if some condition is violated during performing such operations. Common samples are null pointer dereference, division by zero, or double close or of file descriptor. On our sample, the GDM contains the constraints which are put on symbols stored in variables A and B on different execution paths. And also in some execution path, it also stores the state of descriptor F, which is modeled by, for example, a stream checker. CSA can perform interprocedural analysis using inlining method. To do this, it jumps into the first statement of a caller function and then executes it statement by statement. The problem with this approach is that the function is called multiple times. Its statements are reanalyzed again and again. So inlining method is known not to scale well. So the summary-based interprocedural analysis was a desirable option of CSA open project list. The common idea of summary-based analysis is to use the information about function to model its execution in some context. In our implementation, we just analyze the function out of context to form its exploded graph. And we consider this graph as the function summary. And then we extract necessary information from the states of this exploded graph and apply this information to the states of the function call. Summary-based API can simply enable with setting API option of analyzer config to summary, and then we get the exploded graph looking in another way. This graph contains a single exploded node indicating the beginning of analysis, a number of intermediate nodes created by checkers, and some final nodes corresponding to final nodes of Kali's exploded graph. As I said before, we don't collect the summary explicitly. Instead, we just use the final states of program execution. In our initial implementation, checkers were forced to use a special callback, eval summary populate, to create their summary. Now this callback is still present, but its usage is optional, and the callback is almost unused by checkers. Checkers may need to create additional traits in program states to support summary. The common sample is the list of deferred checks that the checkers may need to perform. Before applying a summary, we should note that in the color context, symbolic values have different naming. For example, the symbolic value that was the content of a function parameter now becomes the value of a function call argument expression. So we perform the actualization, which is a discovering of a symbolic value in the color context, which is the mapping for some symbolic value in the color context. The summary application process starts with determining branch feasibility. We ask the solver to perform if some branches are feasible or not. The current implementation of solver used in CSA, Range Constraint Manager, treats the constraints which were put on symbols as a set of ranges of concrete values that symbolic value may have on different execution branches. So the result set of constraint is just a set which is the intersection of a constraint set in the color context and in the color context. If this intersection is empty for at least one symbolic value, this branch is considered as non-feasible, and we do not consider it later. After this operation, we have a set of updated program states which are feasible and contain updated constraints. And then we apply the information from store to them. Store contains the writes to program memory and the invalidation marks. Then we actualize the return value of the function on different branches and bind it to the call expression where the function was analyzed. And finally, checkers participate in the summary application process. In our implementation, checkers are responsible for their own summary. We have made a choice because in general we can predict what logic will be used in check. It may be very complicated, and so we just encapsulate this logic into the checker itself. To participate in summary application process, checker may subscribe a special callback, eval summary apply. In this callback, checkers may use all the operation they usually do. They may split state into multiple, generate exploded nodes and things, and what is summary specific. They also can perform deferred checks and update their state based on the state of the final node. Here is the sample of how checker can apply their summary. We have a small portion of code with the small cali function named close file because of obvious reasons, and the caller function double close. CSA performs the analysis in the topological order, so double close function is called first. If we have a checker that checks for double close of file descriptor, first we encounter the call to fopen function. And checker models this and sets the state of CF descriptor as opened. Then we encounter the call to close file function. We don't analyze it before, so we don't have its summary. And so we stop the analysis of double close function and started the analysis of close file function out of context. We treat the call to fclose function. Now we don't know if the file f was opened or closed during the analysis because the function is analyzed out of context. So we plan a recheck to be done after the analysis done and summary will be applied. Also, we set the state of descriptor f to be closed. After the analysis is finished, we have a single execution branch, and we applied the summary to the point of call. First, we take a look at the list of deferred checks. There is a symbol check for the descriptor f. We actualize it, and the result is the descriptor cf. The descriptor cf is opened on the moment of the function call, so we don't emit any warning. But we set the state of descriptor cf to closed, because it was stated in the callis state and in a separate thread. Then we encounter call to close file again. This function was already analyzed, so we don't analyze it again. We take another look at the list of deferred checks, and we find that a close operation is being called for the file descriptor which is already closed. So we emit a recheck warning. The actualization process needs to establish the relation between symbolic values in Kali context and in Kali context. To perform such mapping, we extensively use the fact that analyzer symbolic value are pretty self-explanatory. For example, if I have a var region, we already know that this is a memory region corresponding to a variable with given declaration, and so on. If a symbolic value references multiple symbolic references another symbolic value, which is a common case, we also actualize them recursively. This is one of the most complicated part of summary application code, but the checker developer could only call a special method actualizes val of summarizer object to get the mapped symbolic value. After the analysis is done and all the warnings are thrown, we should build a nicely looking report. But there is a problem now, because we skipped all the path inside the function and generate only a few nodes. The solution we use is just to keep the reference to the interesting node and the node of the summary application. So we just, to build a path inside the Kali function, we just dragged it up to from interesting node up to the Kali's root of the call graph. And then we glue in this path together, so we get a full path and generate report based on it. From the implementation point of view, the main result we gain from summary-based API is get rid of modeling the environment, which is one of the most time-consuming actions of analyzer. Even if other parts of state, GDM and store, are being repeated in the whole, which is a rare case, we can gain a performance improvement. So more bugs can be found for the same time. This is what we needed, and this is what we finally gained. But there are also some known issues we met. First, the first issue is memory consumption. In the summary mode, we need to keep all the exploded graph until the analysis of the translation unit finishes. So the memory consumption in summary mode is much greater. The second issue is the backside of our solution to in place the summary application logic to the checkers, because checker developers usually don't want to deal with summary. The possible solution is just to smartificate the GDM so it can operate with all the data by itself and without any developer actions. Or just to prepare a set of ready-for-use templates for the checker developer to use. A minor issue is limiting the analysis time. Usually we use max node parameter of analyzer to change the time the analysis is performed. but in summary, the difference between node building times is much greater. So this option doesn't work as expected. Now we use a heuristic with just division and just dividing the max nodes for inlining mode by 4. The other minor issue is the appearance of non-evident warning. The reason is that we don't track the order which our symbolic values are constrained in. So in the moment of the summary application, we already know all the constraints which were not known in the inlining mode. For example, if we have a divide 0 checker, which checks on division by 0, and in call function, divide was used and then checked by 0. In the inlining mode, we will not warn, but in the summary mode, while performing deferred checks, we will have 2 branches, and in the one of the branches, the device will be constrained to 0, so we will emit a warning. And the larger issue, finally, is the modeling of virtual calls and indirect calls, which is not fully supported yet because we don't expect that the function flow may change. To support this kind of operations, we may need to use multiple summaries per function, so it is not supported yet. The second part of our talk will be devoted to inter-unit analysis. Out of the box, CSA can perform analysis only inside a single translation unit. So it doesn't know anything about function definition in other translation unit and cannot use them. These call to functions are analyzed concertedly. So some false positive appears and some warnings are missed. When we started the implementation of XTU, we expected the growth of warnings amount and also improvement of true positive rate for some checkers because the lack of call context is a known source of the false positive. Being a source-based analyzer, CSA needs some special techniques to implement inter-unit analysis. Finally, we came up with the scheme including 3-stage analysis, including the build stage, pre-analysis stage, and the analysis stage, with the AST merging approach. We are not sure if this approach is suitable for other applications, but from time to time I see messages in CFU-dev where the authors want to perform the whole program analysis on the source level, so it may be a nice starting point. On the build phase, a special tool which passes trace utility output launches information collectors for every translation unit. These collectors dump all necessary information we need for analysis, a list of functions which are externally visible for translation unit, functions that need for them for modeling of calls, and also local call graphs. We also dump serialized AST units in order not to repass all the translation units again. On the pre-analysis stage, we resolve the dependencies between functions, and now we know what function definition in what translation unit is placed. Also, we build a global call graph from local call graphs, and we start analyzing it from in the topological order from the upper level. On the analysis phase, we just launch Clang instances in topological order. The analysis is performed as usual, except one thing. When the analyzer meets a function whose definition is not available for him in this translation unit, he made the lookup. And if we can determine that there is translation unit where the function is located, we load this AST unit and import the function definition and its dependencies into our current AST context. And after this, we continue the analysis. After the analysis is finished, we can also generate multi-file report to show how the execution path was going through different translation units. This is a toy example of how a developer may use XTU. First, we should launch XTU build script with specifying it a build command to intercept. After the build is finished, we launch XTU analyze script, which performs pre-analysis and analysis stage. And finally, for our toy sample, we get a single report consisting of two files. The report HTML file is a file where the warning was emitted, and other files, sub-reports, are just highlighted files. Through them, the path was going while performing the analysis. There is also a sample of how the mapping of function is built. We use the mangled name of function and also specify the build architecture. A good point in our implementation is that it don't need the support from the checker side and needs only minor modification of the analyzer. Also, because AST information is merged and it is completely available, we can perform complicated checks, including both path-sensitive and AST-based checks performed together during one analysis run. One of the possible issues may be a limited scalability of such approach. While this scalability is enough for analyzing because we import only a number of translation units per time, building of the common AST of a large project is definitely not the best idea. Another issue we meet is possible name conflicts. For example, if we have multiple functions with the same signature, we may incorrectly determine what function we may need to use. To overcome this problem, we are going to support linker operations. One of the largest issues in the XTU is the usage of disk. AST dumps we collecting during the build stage have large sizes. For example, for Android code, there are more than 70 gigabytes of such dumps. And we were forced to implement the reading of zipped AST units to overcome this problem. And finally, Aleksei team reported that if we're using inlining with XTU, the coverage pattern changes a lot. The inlining is not to scale well, as we know, so many basic blocks in the end of functions become unreachable. However, they reported that even despite of coverage loss, the amount of warnings is still greater. Next two slides contain our internal evaluation of summary and the XTU. To perform such evaluations, we have ported two checkers to support summary. They are const modified and integer flow. And they found not the bugs itself, not the bugs actually, but only places where should we pay additional attention. And the first characteristic we measured was a number of nodes which can be analyzed at some time. For both XTU and single translation unit mode, the summary has a much greater performance, and it can analyze nearly 10 times much nodes per some time. However, as we can see, in XTU mode, the performance is a bit less because of input overheads. And the second characteristic is the amount of warnings emitted per time. In summary, in single translation unit mode, we usually have a limit of warnings which can be emitted. But in this case, we can also see that summary performs greater, and we can set much lesser time to get the same amount of warnings. And for XTU mode, the summary performs much greater in case of large exploded graphs, which was the main target of our implementation. Finally, I want to thank all the people who participated in this work and consulted us and made the evaluation and shared their code. Thank you. That's all for me.
So we have actually quite a bit of time for questions. Does anybody? There's a microphone there, otherwise I can come.
Hi. So have you think about having an inter-module analysis that for each function you would just dump some simple things like for each parameter, like do you use it, like where do you pass it to each functions? So you could just build a call graph of the whole application, and then like it wouldn't, of course, like handle all the cases with the branches and all the stuff, but it would probably find out most of the bugs with use after move and use after free and other stuff like this.
Currently, not all the checkers were ported to support the summary mode. There is an issue we're dealing with.
I don't know.
Did I misunderstand you?
I mean, like, because I see that what you like did is like much more complicated piece of work, and like I'm not sure if like how much. I guess you could find much more bugs with this, and like you could find much more stuff. But like how like is it really needed to find all the bugs or like stuff that like you would like to find?
I think we need to find these bugs. That's all.
Okay, thanks.
So you mentioned that there was problems with name mangling. So if you are importing a function from a different abstract syntax tree and the function has the same signature, or other problems where you're importing functions or symbols with the same name, you may need to implement linker functionality. So have you thought about how to do this? Is there any implementations or anything like this?
There is no current implementation, unfortunately. We're also going to do this. This issue can be met very rarely in projects which have a large amount of translation units. There is the possibility of name conflicts usually appears when we have a build of multiple executables per one build run. For the whole Android sources, we have made this issue only for 2 times. Right. So this is a minor issue, but it may also affect some projects. So I mentioned it.
Thank you.
Any more questions? Okay, so I guess let's thank the speaker again.
Thank you.